Hello. 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 Hi.
Hey guys.
Hi, everyone.
I think we can start. So welcome everyone to this week's tech session. Today, our presenter is Barta, and he will be continuing his series of functional programming. And today we're going to look into the power of the type system. Barta, you can take it away.
Thanks, Plamina. Okay, let's get started. So today we'll continue from where we left off last time. We'll go into a bit more detail about the FP aspects of it, some of the deeper FP aspects of it. There are some warnings though, so I'm throwing around some of these terms rather loosely, and trying to build an intuition, plus trying to demonstrate some code, right? This is definitely not a formal theory class in math, right? So a lot of the stuff I might be saying will definitely be approximately correct, right? But it's a pretty deep subject. It requires a lot of theoretical. It's there on the net. It's a lot of fun, but that's just a warning, right? And then of course, lots of the artwork etc. is stolen from the net, and some of them I may not have attributed, but by default assume that it's all stolen stuff. And the whole idea is here, right? So it's actually pretty fascinating. So this the three talks that I will do here for FP is just sufficient for you to get hopefully excited and then started, right? But eventually it's just finger memory that you'll have to build, right? And that sort of seeps in into your day-to-day working. So you can read all the presentations in the world and you can go through all the videos, but unless you actually try it out, right, you'll never get the sort of the hang of it. So it's a mindset change essentially. And as always, feel free to interrupt me. It'll be a lot of fun if this is a two-way conversation. Other than that, let's get started. Okay, so this is essentially in my opinion, this is pretty much all you need to have excellent mastery over software 1.0, and this is the aspect we're going to cover today, or at least second third of the aspect. The deal here is that as you master, as your system becomes more complex as you go outside, and the more the mastery over these, the lesser the stress is at work, and more focus you can put on the actually solving the business problem, right? And it becomes more fun, right? So this is your skill as an engineer, in my opinion, at least. The other thing is, right, this set of skills is independent of languages, tools, frameworks. These things have been formalized probably since the 60s, 70s. They hold today. They will continue to hold as long as software 1.0 is there, right? But which basically means that mastering these is the worthwhile skill, and not necessarily, Azure Cloud or AWS or React or Angular, right? These are the talks in this series. This is basically the fundamentals, again, in my opinion. Today we'll touch upon the second part, which is the power of the type system. All of these are recorded. Feel free to go through them. Hopefully I can finish this in the next couple of months, or 3-4 months. Can run through this. Right. Of course, the warning. The techniques in this talk definitely have a learning curve, right? Which means that you could potentially get excited and started, but then you would have found that you wasted a fair bit of time before you got anywhere. Try them out in pet projects, right? Or hackathons, pet projects, or some tool that you always wanted to write but didn't have time to write it, right? That's the way to try it out. It's a way to build skills. I'm happy to get in touch with you and collaborate with you as necessary. But make sure that before you try it in your job, you have an approval, right? Your EM has essentially approved that you try this out, right? Otherwise, I don't want to get beaten up by your EM, essentially. Right? So they'll be very grumpy, and they'll complain to. Well, nobody's done that so far. They're all fine people, but I'm pretty sure that basically just get their approval before you try it out in your work. All right. Anybody know who these gentlemen are?
You had the same question last time, but we forgot.
No, those were three other guys. These are two more guys. They are two different guys. Yeah. Okay. The first one is Haskell Curry. The second one is William Howard. And where do they come in? They discovered something called Curry-Howard equivalence or Curry-Howard correspondence, right? Anybody heard of this? This is actually pretty sexy.
Is that like the currying stuff that you can do in like Haskell and stuff?
That's named after Haskell Curry, but that's not what Curry-Howard equivalence or Curry-Howard correspondence is. So Curry-Howard correspondence essentially matches two disparate branches, or at least the branches that were thought to be very separate, right? So it matches propositional logic, and it matches programming. So it basically says they're one and the same thing, right? That's pretty funky. It's a pretty deep statement, right? And what does it mean, right? It means that programs are equivalent to proofs, right? This is all theoretically proven, right? Producing a proof is the same as finding the type of the function, and that has at least one member. True is the unit type, right? For folks that are aware, in I don't think C# has a unit type, but FP, all the functional programming have a unit type. False is a void type, right? This is how you write it in. Void type is essentially a type that has nothing, no elements in it, right? C# you can't do that, right? A product type, which is a tuple or a record or something, is the same as the AND, logical AND, right? Union type, discriminated union, is equivalent to OR, right? The logical OR. And finally, the implication, the logical implementation is the same as a function, right? So pretty much you can see, right, like to have a formal proof of a proposition, you use the ones on the left hand side. And the ones on the right hand side are also what you pretty much use on a day-to-day basis to code up, right? So note the last statement, right? So if you are going to produce a proof that is the same as finding a type that has at least one member, which means if you find if your code returns an exception, which means which loosely means it has no members, there's no type found, then you know that your proof is false, right? So that's the beauty of it, right? So there's a lot of deeper. I've given links into this. You can check it out, right? This is really cool stuff, right? Also, FP can do anything O structured can do, and vice versa, right? You'll need both to be a kick-ass engineer, right? So you can't just say that, hey, I'm an O guy or I'm a FP guy, right? They just help you approach or attack a problem differently, right? How can you potentially mix and match? You can see 13 examples here, but eventually your toolset will build up, right? Eventually you'll find new ways. You can have FP inside O, inside FP, inside O, right? You can have like lots of funky stuff. But the whole idea is to be able to mix and match. So this is not a religious battle that I don't like this religious battle kind of arguments. But the whole thing is that this is just a way to look at things, right? And you have to master both at the end of the day. You have to master mode, but which means to stay out of this stupid online debates, right? FP is better than O, and all this crap you'll often see on Twitter and things like that. It's just not worth it, right? There is a theoretical proof that they are essentially the same thing. So I don't know why people are citing it. Having said that, right, agenda will be, which quick refresher of part 1, then 3 levels of types in FP. This is where we get into the last talk. We covered the basics as well as 4 aspects of function. Today we'll cover the 3 levels of types in FP and some of the very super common patterns, right? These are the 4 common patterns that you will typically want to sort of get a finger memory for, get a feel for, to make you a good FP programmer. And finally, key takeaways and closing notes and so on and so forth, right? If you guys have questions, feel free to stop me. Right. So again, if you want to just browse some real-world functional code, I mean, I took us through a walkthrough of the first one. It's a pretty standard way to write an FP logic, right? But check it out. And the 3 after that are some real-world FP code, right? Those do something meaningful, right? So check them out, right? Specifically, the 3rd one, the 5150 emulator, right? That one has a lot of stuff that we will talk about today, specifically monads and monoids and so on and so forth, right? Sure, right? Last time we saw that the code needs to be able to elegantly handle the real world, namely awkward squad, essentially aspects of the real world that make your code brittle, that push back against your code changing, right? Against your code being malleable, against your code being, so those are the things that become really hard to, which is also gives you something called job security, right? I mean, if they weren't there, then you wouldn't be paid as much. What are they? They are the IO, like taking in stuff from the real world and meaningfully sending out stuff into the real world, right? Error detection and recovery, these are exceptions, such results, timeouts, and all kinds of craziness that the real world is good at throwing at us. Concurrency and parallelism, right? So this is, this is, I mean, our CPUs don't scale up anymore, right? They scale out. So therefore, this becomes supremely important. And then finally, interfacing to external libraries, right? Because you don't know the nature of external libraries, how they're written, how stable they are, what language they're written in, what runtime they're written in, right? So, and you also can't write everything on your own. So you need to be able to interface with other stuff. FP is rooted in lambda calculus. That's something that we saw last time. It's the simplest programming language ever, and the only refactorings that you're permitted, right, are rename and replace. So rename parameters and replace parameters. That's it. right? And an entirety of FP, or at least most of FP is built on that theory, right? And again, lambda calculus is equivalent to Turing machine, is equivalent to recursive function. So this is something that is proven, right? So I mean, there's a theoretical proof for these things, and hence there's no point saying that FP is better than O and things like that. Any questions, anybody? Okay, if not, I'll get going. Right. Again, functions in FP are just like functions in math, just a mapping, right? There's don't think of them as computing something, right? They take an input value from the domain and map it to a codomain, right? And the caveat is that one-to-many is not allowed, right? That's the only thing not allowed. But other than that, just mapping. There's no computation. F of x is sin x. You're just taking x and mapping it to that curve and wherever it hits the y-axis. 4 aspects of functions in FP. Higher order functions, which means functions are as good as types. Right? You can take them as arguments, and you can return them as return types. Currying and partial application, which means all FP functions, just like math functions, have only one input and one output. You build multi-parameter functions. Wherever you see multi-parameter functions are built from those, right? You can compose and decompose them using currying and partial application. Functions in FP are pure and total, so they don't have any side effects. They return values for all inputs and the same value for the same input forever, right? So this is a beautiful, right? So pure and total gives you a nice way to reason about your code, right? So if you look at a function, if you look at the signature of the function, then you can essentially say that for this I'm going to get back this, no matter when I'm looking at it. This is unlike O, where often it depends on the state of your system, what the return values could be, but it's not like that here. Composition techniques are the other aspects. So you'll need to master a toolkit of composition techniques to be able to handle the time system, right? Type system is where a lot of the logic is written in FP, right? So the type system in O is quote unquote pretty anemic, but you can do a lot of business logic encoding in the type system itself, right? So as a result, you don't even have to write code for it. The compiler just handles your business logic for you in a lot of the places. Question so far? This bit is funky. So 3 levels of types in FP. We briefly covered this last time. We had to rush through, but we of course have the primitives, string, int, boolean, and they're just sets, right? So int is a set of 4 billion entries. Int32 is a set of 4 billion entries. Boolean is a set of 2 entries. String is a set of infinite entries, and so on and so forth. Right, infinite elements. Then using this, you build further data types, and this is where the algebraic data types come into the picture, right? So you have a way to compose this and build additional types. For example, you can add 2 types, which means now you get a third type, which is the union of all the types in all the members of int and all the members of bool, which is 4 billion plus 2. Right, or you can have another algebraic data type which is int or int, right? And theoretically it's possible, right? So which means you get 8 billion entries. You could have something called a product type, so you could multiply 2 types, and what it means is that you get back a set which has a pair with 1 each from each type. So you have essentially suddenly composed. I'm going to turn off my video. You've suddenly composed the types, and then you get back a new type that has, it's called a product type. So both have to be there, right? And in the union type, one of them is there, and it's an element of that. And finally, function types, right? So function types are exponents. This is very beautiful, right? And this is also what I was talking about in the proof as programs as proof. Right now, you can use the primitive types and get back additional more powerful types using the algebra, which is sum, product, and exponent. That is just math. Right. So that's the second level of types. The third level of types is something called flavored types. Right. Flavored types is nothing but any of the 1 and 2, either simple types or additional types obtained by doing some multiply, add, or exponent, but with a flavor, with a subtle taste, if you will. For example, right, if T is a type, M of T is another type that is basically T but with a flavor, but with a taste. Right? And what does it mean, right? For example, task of int is an int that you will get back later. Right? It's a flavor of delayedness. Enumerable of int is one or more ints. Right? Nullable of int is an int that may not be there. Right? So you sort of, it's an int but with an additional flavor. Right? Async of int is task of int, and then an option of int or nullable of int. You get the idea, right? Now the whole idea is, right, you want to be able to make illegal states irrepresentable, right? So for example, you can write a type where if you know that your customer's name cannot be more than 20 characters, you can actually write a type with that, where it will just refuse to build the type. It will give you an error type if you try to build that, right? So like that, you can essentially use this algebra. You can use this flavor to make just essentially illegal states, are not even permitted in your program, right? So when your program is running at runtime, you have clean stuff. Anything error, that you can deal with it in another path. You also use the type system to encode the awkward squad, mainly the flavor types you use to encode the awkward types, like IO, then the async, and then interfacing with external libraries. And what is the fourth one? And error detection, right? So you encode the awkward type, and finally, you will be able to freely and cheaply create new aptly named types, right? This is pretty hard in C# or some of the other OO stuff, where you have to create a new file, class, public, static. By the time you get down to this thing, you would have typed in a bunch of characters. So it's not really. However, in functional programs, you are essentially encouraged to create new types. You want to churn out a new type just for the heck of it, do it. Right. So it's made very easy to build new types in FP. Right. Now, these are all not theory. These are very much, you can very much put them to practice. And once you get a hang of it, right, it does change your thinking, and you get back a lot of the benefits. So it's something for you to try. Something for I strongly recommend at least trying this out, or getting in touch with somebody who is like-minded and who's trying this out. Right. It's definitely worth. Right, it may sound a bit abstractish, but that's the whole idea. When you try something out, you see how it's not abstract, how it's actually real, pretty real. It's really real. Right. All right. So we will dive into the first pattern, so to speak. Right. And essentially, this is about dividing and conquering. This is a fancy name. It comes from math, but don't over-index on the name. But the whole idea is, right, if you want to divide and conquer computation, FP has first-class support for this, right? This is one of the common patterns in any programming task, and therefore, it's a generic pattern that you can use when you're writing. It's a first-class pattern in an FP language, right? Now, what does it mean, right? So what's the intuition here? So the intuition here is simple. So supposing you want to do the word count of say 3 pages, so you can combine the 3 pages, right? You can combine the 3 pages and then finally do a word count, or alternatively, you can do the word count of all the 3 and then combine the later, right? Obviously, the benefit of the second one is that you have divided and conquered, right? Essentially, a map reduce. Right, or alternatively, let's say that you computed for page 1 and your computer crashed, right? But you still have that computation stored as the as the count. So your computation is restartable here, right? So those are the benefits of the second approach. Essentially, now if you have an intuition for this, then you have an intuition for monoids essentially. Right, it enables chunking, divide and conquer, map reduce, whatever you call it, incremental computation, restartable computations, which is compute page 1, store the result, then you don't have to compute page 1 again, right? And therefore parallelism, right? What does it require? It requires a type and an operator. So the type here is a page, and the operator is the count. The count of the, or I would say, count of the page is the type here, and the sum, the add plus is the operator here, right? Then operator applied to two values of a type results in the member of another value, right? Which means if you add the count of page 1, if you add the count of page 2, then you get back a count of a couple of pages. It's as simple as that, right? However, this is not the same as, for example, something else, right? You see the average word length of page 1, you can't add it to average word length of page 2. You don't get back an average word length of page 1. So that's not a monoid again. Right, so there's a subtle difference there. So average word length is not a monoid. Average word length plus is not a monoid. However, the word count with addition is a monoid, right? You cannot do chunking with average word count. So you just can't say that I'll compute first the average word length of page 1, and then I will compute the average word length of page 2, and then do the same for average word length for page 3, and then add them out to get the final average. That's not possible, right? So therefore, you see the idea, right? So this is a subtle twist here. However, in the average, what you can do is first you can get the total word count, total number of words, and you can get the so you can get the total length of all the words with the total number of words. Then you can get the same for page 2, same for page 3, then finally add it up and divide it. So that becomes a monoid again. So there is a subtle kind of conversion you can do, right? So what's the C# and F# code, right? It's actually pretty simple. I mean, we've used this day in and day out, right? C# is just as simple as this, right? Aggregate, right? So the whole idea is that sum of this entire sequence is the same as sum of the first 5 elements with that of the 6th element. Right, that's what it means, the aggregate, right? It's a reduce. F#, it's very similar, right? Right, it's just a F# idiomatic way to write the same thing, right? Fold is the same as aggregate here, right? You take 6 elements and then you just fold them up, right? So again, don't over-index on the name. It just means a way to. It just means you're structuring your computation so that you can divide and conquer it, or make it restartable, your computations, right? So that's the way to think about. If you do that, you get the benefits. You get all these benefits. These benefits, right? Chunking, incremental computations, and parallelism. Right. The next pattern, right? Again, don't over-index on the name. It's came from math, but nobody bothered changing it. So then it's like stops mattering anyway. It's basically for iterating over or recursing over data structures, right? And what do you do by recursing over? You typically shape them or reshape them, right? Then, so what's the intuition here, right? So catamorphism is like essentially it stands for two kinds of transformations. Like one is anamorphism, is something you take a type and build another type from it, right? You sort of blow it up. Catamorphism is the reverse. Can somebody give an example of this we use on a daily basis? Like every time you sit down at your computer, you're most likely doing this. Anyone? Okay, so the one on the left, right, the purple box is your source code. Then the compiler runs it, creates an abstraction trajectory, then does a semantic analysis and all kinds of IL generation, and finally when it runs it, it feeds it into the interpreter and gets you a result. So we do that on a day-to-day basis. So the taking a block of text, which is your source code file, and compiling it into generating a syntax tree out of it, is anamorphism, right? You're essentially is essentially when you're just collapsing that thing and executing it, or collapsing that thing and creating another IL or exe, right? That's catamorphism. So you're essentially collapsing that entire thing and generating a final file, right? So that's something that we do on a day-to-day basis. It's pretty, it's not at all abstract, right? It's built up and tear down, like I said, right? And what does it enable, right? It enables traversal over arbitrary abstract data types, right? For example, an abstract syntax tree. Right, if folks know the visitor pattern in O, sort of similar-ish to that, right? And traversal includes iteration and recursion. So typically when you're generating the IL, right, you start from the root node and then kind of recursively go down and generate the IL for each node and finally combine all the IL and dump it into a disk, right? IL or the binary code. Again, this is the example I gave, right? So supposing you were to write a function, evaluate the string 1 plus 2, right? Then 1 plus 2, you will typically parse it to a syntax tree, and then finally you would collapse the syntax tree, right? So first one is, this is essentially catamorphism. What does it require? Obviously an abstract data type and rules for traversal of each node. So if you're familiar with the visitor pattern, right, you get the idea of what I'm saying. But visitor pattern is very, it's very constricted. It's not a generalized thing at all. But visitor pattern is, if you're familiar with it, then you will get the idea of what I'm referring to. Let's start with some C# code, right? So this is a typical, the same thing that I said, right? Summing up an array tree, right? So you can check this out. Why the bullets are coming? So the fold here is an example of a catamorphism. So what you're essentially doing is you are being passed a function combine. This is a generic fold, right? Earlier we saw the aggregate, and this is a generic aggregate for a tree. And in the combine, what you're doing is you're combining the value of the tree, then you're folding the left tree, folding the right tree, and combining all of them, right? And then so therefore, if you're given a tree like this, right, if you want to sum it up, all you can do is boom, boom, and boom, right? So you've essentially taken abstract data type of an array tree with int values and found essentially you summed up over all the nodes. Right, so that's an example of a catamorphism. Right, yeah. So you can use this to map one data structure to another data structure. You can it's a fairly generic thing, right? So catamorphism doesn't necessarily mean destruction. It could also mean mapping of one abstract data type to another abstract data type with a different shape, different structure. Right. So the F# code is also very similar, but it's a bit more concise. Right, it's the same thing. You can see that, you can get the idea. Right, it's basically the same thing. So you start off with a tree definition, then you fold the tree, then inside you write a recursive function, and finally you call the recursive function with identity. Right, and then finally, you get back the sum of all the nodes in the tree. So, and like I said, right, this is not the only way to do it. You can also essentially, it's a generic term for transforming abstract data types, right? In FP, right? Visitor pattern is the closest, in my understanding, in my knowledge, that comes to catamorphism. But catamorphism is much more generic, right? It can handle pretty much any complex data type in FP. These are generic set of rules that you can come up with, that you can decompose or you can reshape or shape the data, right? There are a lot of examples given in F# Fun and Profit. You can can go check them out, or we can do a dojo here sometime in one of the other talks. Then we have something called monads, right? M words. So this is the pattern for encapsulating side effects with a consistent interface, right? Now, what does it mean, right? What the hell does it mean? Okay, so let's start with some intuition first, right? Again, assume a flavor type E of t, right? And E could be task, nullable, enumerable array, and your own personal thing, right? Where you can just say, hey, this is Partha's type. I mean, what I don't know what anybody's going to do with that, but nonetheless, you can create a flavor called Partha's type, right? So just assume there's a flavor type called E. Now, you typically have, I'm sorry, there's a typo there. It should be E of A. So typically you have A as a value in the normal type T, and then you have E of A, which is a value in the type in the flavored world, right? And then you have similar functions in the flavored world. So E of A to E of B, right? So this is essentially the way things look. So there's a way to raise them and there's a way to transform them, right? Map them. But it breaks composition, right? So all this is very nice, but you just, why does it break composition? I mean, typically when you're handling a task or a nullable or enumerable, you're doing it for a reason, because task of int means you don't know when you will get back that int. However, if you're given a function that adds int, right, or two ints, you can't just take a int that you haven't gotten yet and start adding. That's nonsensical, right? So it essentially just breaks composition, right? So monoids and their applicatives is a related pattern. These are patterns to patterns to enable composition of flavor types, right? What you typically do is, right, there's this concept of a bind, and we'll come to that shortly, right? So essentially you write the bind function once for any given type, and then you apply it repetitively, right? It becomes like a sequential. So you can transform a functional looking code into an imperative looking code. Do this first, do that first, do that second, do that third, and finally compose the thing. So in the end, right, you're no longer dealing with the int here, task of int here, but you're actually dealing with task of t. So your impure function becomes a pure expression, right? And then you let the runtime run it, right? So this is essentially, it will require a bit of it will require at least 100, 200 lines of code for you to type it and actually see the, how natural it feels. Right. Let's get to some examples, right? So again, it enables composition of flavored types and flavored functions. And when I say flavor, it also encapsulates side effects. Right, side effects could be when you want to get back something, you may not have it, a sort of a side effect, right? Or when you want to add something to something else, it might throw an exception. That's a side effect, right? So it nicely encapsulates this and provides you a way to handle them consistently. For example, right, given a function a to b, a function that maps say int to string, and given a task of int, you want to get back a task of the string without doing a to result, right? So normally what we do is like, hey, and moment you've done a to result, right, you've just halted the, you've just killed the beauty of asynchronous. So at that point of time, to result essentially waits for you. It stalls the thread, and if it's a long running computation, it probably is going to occupy that thread completely. So that thread is going to be sent to sleep. However, if you're doing async and await, right, it will be the thread will be freed up. The thread pool thread is going to be freed up for doing some other task. And when the input finally comes back, the value of b comes back, your thread is going to be resumed. So you've freed up the threads versus occupied a thread, right? So that is the reason, right? To results. The whole idea is to be able to do these kind of computations without using a to result, or for lists without using a to list, right? Now, what does it require, right? It requires any type that has implementation of two functions, right? And with some stringent conditions, right? Stringent but type independent conditions, right? So something. What are the two functions? One is a way to pack things. So given a, get back e of a, right? For example, for task is given 2, task start from result 2 gives you task of 2, right? And then a way to unpack, right? Now, given task of A, let's see the example, right? So what you're doing here is you're just doing an await of task of 2. So this is a way to unpack, and the way to unpack to result is also a way to unpack, but that way to unpack essentially beats the point of a async computation, right? It, again, like I said, right, it stalls the thread and it kills the threads. Pretty soon it's going to run out of thread pool threads. Right. However, await on the other hand, right, does a bunch of funky things underneath, right? It releases the thread from the computation and then again waits for an IO event to come, and when the IO event comes, it resumes the thread and so on and so forth, right? So await is the way to unpack it in the way that it was meant to be. So essentially what you do is the function signature is like that. Given an A to E of B, you bind it with an E of A and finally get an output of E of B. Right? We'll come to the code for this now. Any questions, comments?
Just a quick clarification. So
Sure.
you need to provide the kind of, let's call it almost encapsulation, the pack and unpack just for the types, not for all the different functions. That's going to be handled for you.
Right.
Okay.
Right. Right. With an applicative, you can also do, there's something called an return. You can do the packing for functions also, but yeah, I'm not going to do the complication. Applicative is a bit of a different flavor, but yeah, you're right. It's only for the pack and unpack. It's in the monadic terms, the pack is called return and unpack is called bind. But pack and unpack are intuitive ways to name them. Had anybody not heard of monads before this talk? You guys heard of it, huh? It's pretty cool. So monad C# code, right? So let's take a very trivial code, but you get the idea, right? You can. I mean, we've used this on a day-to-day basis, right? So let's say there's an A, there's a B, and now you cannot do it breaks composition. We cannot do A plus B as B works with only ints and not task of int. So what do you do is you await A, await B, and then what you get back is a task of 3, right? And later on you can go await that and get back, right? Or even better, you can give it to the runtime. For example, if it's an ASP.NET Core controller, you can just return the task of T and it will handle it for you, right? It will do the right thing in terms of pulling out, unpacking the 3 and sending it back to the network. You don't have to deal with the 3 at all in the entire pipeline. So that's the beauty of it. So there's anytime you're writing toList or toResult or any of the 2 functions, right? You're getting into trouble. I mean, you're just beating the point of a monad, right? So that's a red flag. Anytime toList or toResult, those are like red flags. Or C#, right? For async, for handling async, we have async and await. So for handling tasks, we have async and await in the language built into the language. For handling IO enumerables, we have link built into the language. You have a bunch of keywords and things like that, right? For options and nullables, we have the coalescing operator and the conditional access operator, right? But the ugliness of this is, right, this is very highly inconsistent. So essentially, we're dealing with flavored types, right? Which means for each different flavor, we have to learn a separate language syntax and a separate way to handle. Like some of them are keywords, some of them are operators, some of them behave differently, some of them are something called a link. They behave like SQL statements. It's very inconsistent, right? So essentially, what we're doing is we're composing flavored types, right? Either it's a delayedness or multiplicity or optional, right? But for each of them, we are essentially having to learn new ways to handle it, right? So that's what makes imperative code not very friendly for handling or encapsulating, computations or side effects, right? However, that's not the case with FP, right? FP, this has been elevated to into first class citizen through the concept of a monad, right? Monad. What does it look like, right? So it's the same thing. First 2 lines are the same. Again, can't do this thing. What we can do now is we can say that I'm going to add B, which is this is a way to the plus is a function, and if you call the function with 2, you get back a function with single parameter, which if you call later on with another parameter, you just add 2 to it, right? And then finally you return async. So essentially this is the input of the bind. Here if you do async.bind with add B, you get back the same result, async of 3, right? Now the beauty of this is, right, it will require some getting used to, but the same code, right? Just replace async with option, or just replace async with list, or replace async with maybe, or any of the other monads, right? Just replace them with that. The same code will work, right? So if it's an optional int, then, and if b is null or none, then the sum in the end is going to be a none, right? But the code is going to look exactly the same, right? So that is the. Sorry, go ahead.
Yeah, could I have a quick question? In this
Sure.
case, isn't it like hard coded though, or am I missing? Because like in this case, if we say let b is return 4, then it's still going to return 3, right? Because we're just adding 2 dot b.
You are correct. I took a shortcut here. You're absolutely correct. You're absolutely 100% correct, right? What you can do here is, right, you can add a, so this gets into applicative. So you can have a function called add generic, where you can pass it 2 parameters, and then you can create add b from there.
Oh,
But you're 100% right? So this is a bit of a shortcut I took because I couldn't find a good example that will fit in like 4 lines of code that can show, you know, a very simple operation like this. So I had to take a bit of a shortcut, but well caught, right? Pretty nifty that was. But you're right. But it's an easy transform to make there, right? You can just add another function which is add, and then, you know, and return and take in another parameter.
Right.
But 100% right. Right. Now, coming back to the point here, right? Unlike in imperative languages, where you have to handle the computations, and each type of computation has a different keyword, different way to handle different semantics, and different learning curve. In any functional program that you, any functional language you write, they're all handled the same way. They are monads at the end of the day, right? So you learn once, and you learned it for all the computation expression. There are subtle twists, like they have to satisfy certain conditions and things like that. But I think that is the easier part to handle. But the consistency, which means you learn once, you learn one of them, you learn them all, right? Now, I should probably speed up. Now, of course, this is just the tip of the iceberg. If folks are interested in knowing more, you know, there is a bunch of other patterns here, and most of these have a lot of good usage. Most of these should be used, are pretty frequently used, but there are some, you know, some very esoteric ones, right? Arrow plus, arrow 0, and so on and so forth, that at least I haven't needed to use, right? But once on the top left and the center, foldable is, for example, catamorphism. Applicative functors, monoids are all, you know, side effects, right? Each this is a nice zoo of you know, the patterns that I just touched upon. Had anybody seen this diagram before? It's actually pretty famous. Anyway, nonetheless, check it out. It's in type classopedia. It's also called the zoo of. It was named by one of the FP guys, the zoo of. Right. Okay. So finally, right, the fourth pattern is the actors. Not this guy. This one. Right. Now, the whole idea here is, right, you want to be able to do parallel computation, and parallel, you want to be able to utilize your multiple CPU cores, you know, 256 or 1024 CPU cores. But you want to do it in a pure functional manner, which means you can't have side effects. You must have total and pure functions, and which means you can't share state, right? So those are the constraints. So that becomes parallel processing, where you don't have a global state to share, and, you know, you have to return value for everything, and, you know, it becomes a bit, you have to think about it a bit differently, right? And your processing functions are pure, right? It makes the thinking a little bit, but the deal with this is, right, this is originally from Erlang. Have folks used actor library or the akka.net? Has anybody used it here? Just curious. All right, so this one is actually, it's pretty funky, right? It's designed long time back, right? And the deal is they reported like 9.9 uptime. That's just unthinkable. Like, what does it mean? If you have one machine, then that's 3 seconds of downtime per 100 years. Let that sink in. right? So these are telephone switches, which means they have to keep running. You can just say, oops, my telephone switch crashed, right? So this is actually pretty cool. This entire the way to deal with this is improvise there, right? And you know, this is potentially what you can achieve with some skill, right? What's the intuition? They are essentially basically functions running in a loop waiting for a message. That's it, right? The functions are pure and total because they are FP. The whole idea is they receive an input message, perform computation, and send an output message, right? And the input comes from the framework and the output is sent to the framework. You never get to deal with another actor, right? You can target actors, you can send messages to actors. This is essentially similar to Windows message loop, right? You can send messages to actors, but you have to send it through the framework, right? You are not allowed to share state and you can't see the state of any other actor, right? And which also means that you can spawn as many as you want. It's completely elastic, right? You can spawn as many as you want. You can distribute the load. So all that is taken care of by the framework for you. Again, no shared state between actors, right? And interaction between actors through async messages only, right? So parallelism and async is rather async is built in, right? And actors can hold only pure state, right? So you can't have a state, you know, stored somewhere else in the system that you can go, you know, modify. So that's not possible, right? So each actor has its own state isolated, right? And that's why you can see the processing heap. It's like a isolated for that particular actor. And given that they're very cheap, you know, very low cost, cheap, you can even spawn as many of them as necessary. Depending on the load, you can spawn more, or if the load dies down, you can spawn less, and so on and so forth. Right. So all the scheduling aspects of it are handled with the runtime for you. So all you need to do is write pure and total functions that hold pure state, and you essentially pass it on to the you know, wrap it up with the framework constructs and pass it on to the framework. Right, the framework handles it for you. Right. Check out aka.net. This is a standard, pretty state of the art library for .NET. It's full first class support for C# and F#. F# is a bit more idiomatic and you know, it's nicer to look at and more in tune with the language. C# you have to fight it a little bit, but it's still doable. You can get the same benefits in both. Right, so you can potentially, so the whole deal is that whatever examples I've shown, they're all possible in C#. It's a bit clunky. Right now, I think that's pretty much it. So key takeaways with the functions and the types. These are, like I said, right, these are the very basics for you to get started. And this is hopefully for you to get interested. And if you have ideas, and if you want to, obviously, I have to work with use with only EM approval, right? Don't get my ass kicked. But if you are interested, right, we can certainly pair up on something, pet projects, or you know, happy to pair up with you. This is all a lot of fun. Right. The goal should be that don't think about whether your code is looking good or not, so on and so forth. Just get to 5,000 lines of code as quickly as you can. Right. The fact that once you get to the 5,000 lines of code, right, some of this will just start sinking in. So once it sinks in, then it becomes part of you. Right. Study others' FP code. Again, and finally, right, if you are writing a functional, attempt to capture as much of the business logic in types as opposed to code. Right, that gives you a nice way to sort of mentally, you know, work with types. Right, so a lot of the error conditions and a lot of the errors in the program can just rule it out by creating types. Well, that's the leftover from previous one, but talk 3 we can do some real world code walkthrough, or if somebody has a piece of code that they want to write in FP way, we can do that as well. As I told you, you know, that'll be fun. References, there are some getting started. I would recommend just the first is good enough for you to get started, but domain modeling made function is also a pretty cool one. And then Haskell, yeah, you can go there if you want, but yeah, it's a good language. So there are some real world code, check it out. And then finally, Simon Peyton-Jones is a Microsoft guy. He's one of the contributors, one of the inventors of Haskell. He's in Cambridge. Say hi to him on Teams. pretty much it, I think, from my side. That's pretty much it. Any questions? Any discussions? It'll be fun. There were some comments on the chat. Yeah, higher kinted generic types in .NET will be fun, and that's one of the reasons why F# doesn't have it.
Hey, Partha, it was a very nice presentation. I was just wondering, do you have any like real case where you use actor pattern, like some particular usage? I mean,
Anywhere you need to do parallel computation, you can earlier normally in .NET, what you do is you spawn a async await and then wait for all or wait for any, right? Those kind of stuff you can just rewrite them in Akka, rewrite them in the actor pattern. It's the same thing, right? It's a bit more resilient and a bit more functional, and therefore a bit more. It's a bit harder to get it wrong, but anywhere we do an async await, it's a candidate for Akka. Did that answer?
Yeah, I was just like wondering because there is like this service fabric which is provided by Azure, which also supports like this programming model, like the actors, but it's like distributed across the whole cluster. And actually, because one thing it gives you like this possibility to use the resources. On the other hand, there is the like a limitation that the actor always runs in single thread, which like can be like, you know, advantage and also like a disadvantage in the same time. So I'm just like, you know, wondering like, you know, like in some real scenario like where it really like where if you have any like really hands-on experience like working with that, because I don't, and like I'm curious.
No, actors I haven't, like I don't have a production code that I've written actors. I've written a bunch of pet projects and so on and so forth, but no production code yet. Right, all my production code is still async await.
Okay, thank you.
Okay, thanks guys for attending the talk.
Thank you, Partha, for presenting today's tech session and for everyone for joining. If anyone wants to fill back the feedback form, if you want to present in the next tech session, please do so, or what you want to see. So yeah, applause again for Partha, and see you next week. Bye-bye, everyone.
Thanks. Bye.
Bye bye.